We will review here that the reason why GNNs outperform graph filters is that pointwise nonlinearities move high-frequency components into lower parts of the spectrum, where we can use stable filters to discriminate them at deeper layers of the GNN stack. Since the nonlinearity is pointwise, it is impervious to changes in the shift operator. Therefore, the same stability theorem that holds for graph filters also holds for GNNs if we consider relative perturbations modulo permutation and individual layers that are made up of integral Lipschitz filters. We can establish the stability of GNNs relative to the norm of the perturbation. The stability constant is essentially the same, except that it is scaled by the number of layers because the error propagates, the error accumulates. We say that the stability of the GNN is inherited from the stability of the graph filter, because it is due to the stability of the filter that the GNN is stable. A fact we can state in contrast to graph filters is that it is possible to discriminate high-frequency components with a stable GNN. This is because the GNN inherits the stability properties of graph filters. This is good. Having stable learning is useful, necessary even. But GNNs do not have to inherit the bad discriminability properties of graph filters. They can rely on pointwise nonlinearities to demodulate high frequencies into low frequencies, where they can be discriminated with a stable filter at deeper layers. To explain this latter statement, consider the problem of discriminating signals xi and xj that are aligned with the eigenvectors vi and vj of the shift operator. In the GFT domain, these signals are represented by spikes at eigenvalues lambda I and lambda j, which are the corresponding associated eigenvalues. Since we are assuming that these eigenvalues are large and that we want to have a stable filter, we can't have a filter that separates them perfectly, but we can have a filter that isolates them from the rest. If we hit this filter with input signal xi, the output is a scaled version of Vi. The scaling coefficient is the filter's response evaluated at lambda I, which is a value close to 1 in the example shown. If we hit the filter with input signal xj, the output is a scaled version of Vj. The scaling coefficient is the filter's response evaluated at lambda j, which is also a value close to 1 in the example shown. The filter isolates signals Vi and Vj from the rest, but, very importantly, it does not discriminate between them. It cannot if it is to be stable. And this filter is one that is stable to deformations. Indeed, if we consider a scaling of the spectrum, the filter's frequency response is instantiated at dilated eigenvalues. But since the filter is integral Lipschitz, the dilation of the eigenvalues doesn't change the value of the filter's response. If we hit the filter with signal Vi, the output is still close to Vi, because the filter's response evaluated at the dilated eigenvalue lambda I hat is still close to 1. The eigenvalue has moved substantially, but the integral Lipschitz condition has kept the filter's response unchanged. Likewise, when we hit the filter with signal Vj, the output is still close to Vj, because the filter's response evaluated at the dilated eigenvalue is still close to 1, because even though the eigenvalue moves, the filter does not, because it is integral Lipschitz. The filter is stable, but it does not discriminate between Vi and Vj. Here is where the nonlinearity and deeper layers come into the picture. When we apply the nonlinearity to the output of the filter, we obtain spectral profiles for sigma of Vi and sigma of Vj that spread energy across all frequencies. More to the point, suppose that the input to layer 1 is the eigenvector Vi. As we explained in the previous slide, the output of the filter at layer 1 is roughly Vi itself. It gets scaled by a frequency response close to 1. We then apply the nonlinearity sigma to compute the output of layer 1. The projection of sigma of Vi on the spectral domain of the shift operator yields the GFT V Hermitian times sigma of Vi. This is represented in this figure for the shift S and for the dilated shift S hat. The very important point here is that since the filter in layer 1 is stable to dilations, the output of layer 1 is more or less the same, whether we run the filter on the graph S or we run the filter on the dilated graph S hat. Analogously, when the input to layer 1 is the eigenvector Vj, the output of the filter is roughly Vj itself. It gets scaled by a frequency response that is also close to 1. We then apply the nonlinearity sigma to compute the output of layer 1. This is therefore sigma of Vj, more or less. The projection of sigma of Vj on the spectral domain of the shift operator yields the GFT V Hermitian times sigma of Vj. This is represented in this figure for the shift S and for the dilated shift S hat. As is the case when the input is Vi, the very important point here is that since the filter in layer 1 is stable to dilations, the output of layer 1 is more or less the same, whether we run the filter on the graph S or we run the filter on the dilated graph S hat. Thus, energy at the output of layer 1 is spread across several frequencies in a manner that is stable to deformations. Layer 1 outputs are the same if the filters are instantiated on S or the dilated S hat, and their spectral representations have components at all frequencies. In the case of both signals, some energy is where it used to be. Some energy is at other high frequencies. Some energy moves to medium frequencies, and some energy moves to low frequencies, the latter of which can be discriminated with a stable filter in layer 2. We should remark that these two are actual GFTs of nonlinearities applying to the two largest eigenvectors of a random graph with 8 nodes. Their frequency components have a certain garbage aspect to them, but it is a stable garbage. It can be discriminated with stable filters, and the process can be repeated. We can isolate again high frequencies with a stable filter and process them with nonlinearities so that we can discriminate them better at layer 3. Fact indeed, it is possible to discriminate high frequency components with a stable GNN. A GNN can be discriminative and it can be stable at the same time. Stability and discriminability are compatible. Individual layers cannot discriminate high-frequency components. They must use integral Lipschitz filters if they are to be stable. But nonlinearities are low-pass. They demodulate high-frequency components into low frequencies. All common nonlinearities reduce variability. They are low-pass demodulators. And in moving energy to low frequencies, they enable a stable discrimination. They enable a legitimate trade-off between stability and discriminability that is impossible to attain with graph filters.